Welcome to this explainer. Okay, today we are going to dive into a massive paradigm shift in how we think about system design. We're exploring the fascinating and honestly pretty mind-bending transition from static data to the dynamic, unbounded world of stream processing. For the longest time, we've treated data like a stagnant pool, a reservoir that we just check in on occasionally. But modern architectures, they're learning to treat data like a continuous, never-ending river. Think about it. If your business is always on, your data quite literally never stops, and your infrastructure fundamentally needs to reflect that reality.
To guide us, we're grounding our journey today in some foundational insights from the iconic text, Designing Data-Intensive Applications by Martin Kleppmann and Chris Riccomini. If you spent any time in data engineering, you probably already know the leaping wild boar on the cover. It is basically the definitive guide for demystifying the complex infrastructure powering modern data systems. Specifically, we're going to synthesize the incredibly rich concepts from Chapter 12 on stream processing. This chapter is an absolute game changer because it fundamentally redefines the entire relationship between databases and messaging systems. So ask yourself this: what actually happens when your data never stops? Traditional batch processing operates on a really comfortable assumption. It assumes data has a clear beginning and a clear end. It assumes we can gather up, say, a day's worth of data, process it all overnight while everyone is sleeping, and be totally done by morning. But in the real world, with continuous user interactions on a website, high-frequency financial trades, or the staggering volume of sensor readings pouring in from IoT devices, data flows continuously. It doesn't neatly stop at midnight just so we can run a convenient analytics job. Here is the crucial difference. Batch processing is all about handling fixed, historical, bounded data. You're crunching it in massive chunks, which means you often have hours of built-in latency before you actually see any results. Stream processing, on the other hand, tackles the unbounded chaos of events arriving continuously. It pushes our reaction times down from hours to seconds, or even milliseconds. It allows our applications to respond to changes in the data almost immediately, rather than making impatient users or critical business systems wait for tomorrow's batch run. Here's our roadmap for this explainer. First, beyond batch processing. Then, transmitting the event stream. Databases as event streams. Reasoning about time. Joining unbounded data. And finally, surviving system failures.
All right, let's jump right into part 1, beyond batch processing. Instead of parsing a massive static file line by line, stream processing relies entirely on something called events. Now, what is an event? Well, it's a small, self-contained, immutable record of an action. You can think of it as a historical fact. It happened, and you absolutely cannot change the past. In streaming terms, this event contains a payload of what actually occurred and usually a timestamp of when it happened. It gets generated just once by a producer, like a mobile app or a web server, and then is processed by multiple different consumers in a publish-subscribe model. The beautiful part is that consumers don't have to constantly poll the producer asking, "Hey, anything new?" This is a massive, massive departure from traditional databases where we just overwrite old rows with new information.
Moving right along to part 2, transmitting the event stream.
So if we have all these producers firing off events, how do we get this data from point A to point B without losing it, especially when producers are blasting out data way faster than consumers can handle? We solve this with message brokers. But there is a giant difference between the two main types of architectures here. Traditional brokers, using older standards like JMS or AMQP, view messaging as a totally transient operation. The second a consumer says, "Got it, processed it," the broker deletes the message. Poof, gone. That is really dangerous if a consumer crashes halfway through, or if you ever need to derive new data from old messages, because that historical data is just gone forever. Log-based message brokers fundamentally shift this paradigm. They use append-only shards to durably store messages on disk. They retain them just like a database would, rather than throwing them in the trash.
When you look at how a log-based broker, like Apache Kafka, for example, actually works, it's pretty brilliant. The data topic is broken down into separate partitions. Within each partition, messages are strictly ordered, and the broker assigns a monotonically increasing sequence number to every single message. We call this an offset. Writing sequentially to disk like this is incredibly fast, and because the broker retains the messages, consumers just track their own progress using these offsets, kind of like a bookmark. If a consumer crashes, no big deal. It simply rereads from its last recorded offset when it reboots. You can even hook up a brand new consumer and it can replay the entire history of the log from day one. Imagine the possibilities for spinning up new analytics or debugging historical issues. It's a real game changer.
Okay, part 3, databases as event streams. This is where things get really fun. For decades, engineers relied on application code to do what we call dual writes. You write to your main database, and then you immediately write to a search index. But what happens if the network suddenly drops, right after the database write, but before the search index write? Well, your search index never gets updated. Now you have race conditions and completely out-of-sync systems. It's a nightmare. Enter Change Data Capture, or CDC. With CDC, we observe every single insert, update, or delete happening at the database log level, and we extract them, turning them back into a flowing river of events. The database becomes the absolute single source of truth. This new stream can then be consumed in real time to update external search indexes, invalidate your caches, or feed your data warehouses. It ensures all your systems stay perfectly in sync without relying on super fragile dual write logic in your app.
There is a really beautiful mathematical duality at play here. When you think about it, your current database state is simply the integral, the accumulation of all historical events over time. Conversely, a stream is the derivative of state. It represents the constant flow of changes. Mutable state and an append-only log of immutable events, they aren't opposed to each other at all. They are literally two sides of the exact same coin. A database table is actually just a cached, materialized view of an event log that has been applied up to a specific point in time. Mind-blowing, right?
Let's transition into part 4, reasoning about time.
When data never stops flowing, how do you define the last 5 minutes? This brings us to a deeply philosophical but highly practical problem. Let's say an event is generated on a mobile device, but that user's phone goes offline in a subway tunnel for 3 days. When it finally reconnects, do we trust the event time, the timestamp when the user actually clicked the button underground? Or do we trust the processing time, the time our server finally receives the event 3 days later? And what about straggler events? How long do we keep a time window open waiting for delayed events to arrive before we just finalize our calculations and move on?
Let me tell you, relying on processing time is incredibly dangerous. Imagine you have a perfectly steady stream of requests. If your stream processor restarts or experiences a network hiccup, it builds up a backlog. When it wakes up and churns through that backlog all at once, windowing by processing time creates a massive false spike in your analytics, a spike that never actually happened in reality. It's kind of like watching the Star Wars prequels. If you watch them in processing order, meaning their release dates, the narrative timeline is completely ruined. We absolutely must build stream processing systems that respect true event time, grouping events by when they actually occurred in the real world, even if they arrive wildly out of order.
To properly aggregate this continuous data, we group these events into time windows, and we have a few different options for how to do this. We can use tumbling windows, which chop time into rigid, non-overlapping blocks, like calculating total sales from exactly 10 o'clock to 10:01, and then 10:01 to 10:02. We can use hopping windows, which give us a smoother picture by overlapping these fixed periods, really useful for rolling averages. Sliding windows group events that happen within a specific interval of each other. Or we can use session windows, which are totally unique to streaming. Session windows don't have a fixed time limit at all. Instead, they group bursts of user activity together, like someone clicking around an e-commerce site, and they only close the window when the user actually goes inactive for a set period.
Which brings us to part 5, joining unbounded data.
So once we have our streams and we've set up our time windows, how do we combine these endless rivers of data together without completely running out of memory? Well, we use 3 primary types of joins. First up is the stream-stream join, also known as a window join. This is perfect for finding related events across different streams, like matching a user's search query with their subsequent click on a result, as long as it happens within, say, a 30-minute window. Second is the stream table join, which is all about stream enrichment. Now, if you query a remote database for every single incoming event just to get a user's profile details, network latency will absolutely destroy your throughput. Instead, the stream processor keeps a continually updated local hash table copy of the database. And how does it keep that local cache fresh? By subscribing to a CDC stream of the database. It's genius. Finally, we have table-table joins. These consume 2 database change logs to continually maintain complex, real-time materialized views. It's exactly how your Twitter timeline stays updated the literal instant someone you follow posts a new tweet. Finally, part 6, surviving system failures. Here's the truth. Systems fail. Networks drop, machines crash.
In batch processing, if a job fails, you just restart it from the beginning of the file. But you obviously can't restart a years-long continuous stream from the beginning. So to survive, systems use advanced techniques. Frameworks like Spark Streaming use microbatching, which breaks the infinite stream into tiny 1-second batch jobs. Frameworks like Flink use rolling checkpoints, periodically saving the exact state of the operator to durable storage. And the real magic happens when you combine these with idempotent writes. Idempotence is just a fancy word for operations that produce the exact same result whether you apply them once or 10 times, like setting a value to 5 rather than incrementing it by 1. By doing this, systems guarantee effectively exactly once semantics. So even if a crash causes an event to be processed multiple times during a retry loop, the final effect on your system state is exactly as if it was only processed once.
I absolutely love this quote from the text. The log of all changes, or changelog, represents the evolution of state over time. It beautifully summarizes our explainer today. Mutable state and immutable events are simply two sides of the exact same coin. By embracing the event log as the foundational source of truth in our systems, we unlock this incredible ability to rebuild states from scratch, maintain incredibly complex asynchronous caches, and decouple our massive, data-intensive architectures so they can effortlessly scale to handle real-world demands.
So, I'll leave you with this. As you think about the architecture of your next data-intensive application, really consider how embracing unbounded streams might completely transform your approach to system design. Unbundling your database and treating data as a continuous, flowing narrative of events, rather than just a static snapshot, gives you unparalleled flexibility, resilience, and speed. Thank you so much for joining me on this deep dive explainer. Now go out there and let your data flow.